Okay. The last thing in lesson 1.4 is called the squeeze theorem, and it's kind of cool. What it's talking about here is you have three functions, all right, where one of them is always in between the other two. All right, they're saying that right here. G of x in this picture right here. G of x is always between h of x and f of x. Okay, could be equal to them, but is always between them. So as g of x is coming along, right, and then it's always in between them. So here's the thing then. So if this is the case, and then f of x and h of x share a limit, all right, we're seeing that right here. F of x and h of x share a limit at a particular c value. Well, g's got to go there too because he's always squeezed in between them, right? So over here, sure, he's got some wiggle room. He can move around and stuff because h of x is way up here and f of x is way down here. But if h of x and f of x come together, well, g of x is said to always be between them. So he's got to go right through that little gap right there, squeezed in between them. That's the reason for the name of the theorem. So it has to happen that that his limit g of x will be the same as h of x and f of x. Okay. So example A then. All right. It says f of x is always between 1. So that's just a horizontal line. It's always 1. And x squared plus 2x plus 2. Well, of course, x squared plus 2x plus 2 is not always equal to 1. So guess what they ask you then? All right. What happens to f of x then if it's always in between those two, and if 1 and x squared plus 2x plus 2 are the same at this moment? Well, that's what we've got to find out. Okay. So obviously, the limit, yeah, blue's good. All right. So the limit as x approaches -1 of 1, so I'm dealing with that one, is 1. All right. And so then if I can prove then that x squared plus 2x plus 2 has the same limit and f of x is in between those two all the time, it's got to have the same thing. All three of them will have the same, just like right here. All three of them have the same limit. All right. So here we go then. So the limit as x approaches -1 of x squared plus 2x plus 2, slow down, equals -1 squared plus 2 times -1 plus 2. Okay, so that's 1 minus 2. So 1 minus 2 is -1. -1 plus 2 is 1. All right. All right. So then you would say, all right, therefore, I'll write it. No. No, I can't. I'm going to, got too much math notation. All right. So here we go. Since 1 is less than or equal to f of x is less than or equal to x squared plus 2x plus 2, and the limit, this might be overdoing it, as x approaches -1 of 1 equals the limit as x approaches -1 of x squared plus 2x plus 2. By the squeeze theorem, I'll just keep going. The limit as x approaches negative 1 of f of x. Oh my gosh. Also equals 1. Okay. All right, that might have been a little bit overkill on the explanation. All right, let's look. I'm gonna look at her key and just see what she says on that. Okay, I went a little too wordy there at the end. After no, it's still the same. Since the limit, I said the same thing. Then by the squeeze theorem, the limit f(x) is approaching 1. It's not it's the same thing. Okay, let's see if we got another one of those. Oh yeah. Okay, so we said it says suppose f of x and g of x are boundaries of x h of x as shown. Oh, okay. So it's not exactly the same thing, but because this time the red one, sorry, I was pointing at the screen with my hand. The red one is below and then above, and then the blue one is above and then below this green squiggle, right? So so it's still the squeeze theorem because they're intersecting, and h of x is always in between those two, but but in a different order. So like on the left hand side, it goes largest to smallest, blue, green, red, and on the right hand side it goes red, green, blue. But it's still the same idea, right? So this green one is stuck in between, and then when they intersect, it's got to intersect too. Okay. So I'm just curious and we'll just look at her wording on this one, just so I don't go too far this time. Okay. So, oh my gosh. Oh my gosh. All right. So she went completely nuts on this. Okay. Listen, don't take notes on this one, because if you did have a free response on something like this, I just can't imagine you having to put all of this. But I still want to work my way through it. All right, so this is what we already said. So it says part one, the limit. It says suppose f of our boundaries is shown given that f of x is this crazy equation. All right, so that's the red one, and then the blue dotted one is e to the x minus 1. Okay, for all containing x equals 1 except the possibility of x equals 1 itself, find the limit. Okay, there we go. So first of all, they're showing that their limits are both 1. Okay, so the limit as x approaches 1 of f of x is 1. All right, so they substituted in, and g of x is 1. And then for the less than, this is what we said. For the less than one, it went blue, green, red, and then they did from the left. Okay, and then on the right hand side, it was red, green. Yeah, right. Red, green, blue, and they approached the limit from the right hand side rather than left hand side. Okay, so then they said, okay, so since these two limits as you approach from the left and the right of h of x are both 1, then by the squeeze theorem, it's 1. Okay. Wow. All right. Don't write that down. Don't write that down. I just want y'all to see that squeeze theorem could be used in multiple representations. Okay. That one's pretty out of hand. Okay.